Hey everyone, welcome back to Everything is Relative with me, Mr. K. Today we're going to be looking at Cambridge AS Physics, and we're going to be doing a crash course on the topic of DC circuits. So for those of you that may have done electricity before, there might be some familiar concepts here, but for others this may be new stuff. And so we first start on the topic of DC circuits with the subtopic of circuit symbols. So when we work with electricity, it is more efficient and much easier to represent components that go into an electrical circuit by symbols rather than drawing the device or the meter each time. So there are common components that are always existing in an electrical circuit, and so we can represent them with symbols which everyone around the world shares, so we can share the componentry of an electrical circuit with one another. And it also illustrates easily how components interact with one another. So the first component, probably the most important or the most basic, is the cell, the power source of a circuit. So a single cell is going to supply power, and the symbol for a cell is two parallel lines, one longer than the other. And the longer line is usually the positive, and the shorter line the negative. Sometimes those plus and minus signs are drawn in, but they need not be. We just have the convention that the longer line is positive and the shorter one is negative. If I connect many of these cells together in series, then what I have is what I call a battery. So it might be confusing. You might think of a battery as just a single thing, but in circuitry we consider a battery to be a collection of cells, multiple cells, and they are lined in such a way that they are represented each by these two parallel lines. Next we have a switch, which, as you may have guessed, a switch can be open, as in the case I have here, meaning there's a break in the circuit, there's a gap in the circuit, and current cannot flow. And basically, as you can infer from the word switch, if I close the switch, current can now flow. So I can turn the switch into an open position or a closed position, which will mean the current can flow or not flow depending on the position of the switch. Next, I have a lamp, which is a type of resistor, has a high resistance and will give off light energy and possibly some heat energy as well. And a lamp is a circle with a cross in the middle. Now you may come across some symbols in other textbooks and resources that look slightly different, but these are the commonly used international symbols. The newer symbol for a fixed resistor is a rectangular box. So anything that resists the flow of current is called a resistor. And if we place a resistor whose specific job it is to resist current into a circuit, then it will be represented by this rectangular box. And that's a fixed resistor, meaning its resistance cannot be changed. If I have a resistor whose resistance can be changed, then I call this a variable resistor, which is the same symbol as a resistor, rectangular box, but now with an arrow moving through it to the upwards and to the right. And this is called a variable resistor. And so this is something that will resist current, but we can vary the amount by which it resists current, and this is a variable resistor. So I'm not going to go through all the circuit symbols because we'll be here a month, but just the most common ones that we are likely to see in this crash course or in this topic. But my suggestion would be to go through all that you have in your textbook and understand them, because any of them could appear in an exam question. Next, we have the thing that's used to measure current in a circuit, an ammeter, where the word ampere comes from. An ammeter measures current, and it's usually connected in series and represented by a circle with the letter A in it. And lastly, a voltmeter, which is always connected in parallel across two different points in a circuit. A voltmeter is a circle with the letter V in it, and it is used to measure the potential difference between 2 points in a circuit, or the voltage. Those two words we can use interchangeably. And so this is called a voltmeter. And so these are some of the symbols that we're going to use. Again, there are others like diodes, etc. But as you page through your textbook, you will see these symbols, and it would be a good idea to learn as many as you can. So where do we start in this topic? Well, we start with the electromotive force. So again, this might be something you've heard of before, or it might be something completely new. Now, it is called a force, but it's actually not a force. We also call it the EMF, and it's short for electromotive force. So the EMF is the amount of energy that goes into an electrical circuit. So basically, how we define the EMF is the energy that is transformed, or rather comes from other forms like chemical, etc., and is given to the electrical charges as they flow through the circuit. So quite simply, I'm going to lazily say this as the energy from other forms that is then converted to electrical in an electrical circuit. So the chemical potential energy in your battery, for example, that is given to the charges in the circuit per unit charge. So that energy divided by the charge is called the EMF. Well, you're probably wondering, how does this differ from potential difference then? Well, they are measured with the same units, that is the volts or the volt, but the potential difference, we'll sometimes refer to this as PD, again, just out of laziness. But PD, potential difference between 2 points in a circuit, is the energy transferred from those charge carriers, which it got from the source, the EMF, to whatever device in the circuit it is transferring the energy to. For example, if we were thinking about the lamp that I mentioned earlier, then the energy was being transferred into the form of light and a bit of heat, depending on what kind of lamp it is. The energy transferred per unit charge. So if I were to draw a very simple circuit, let's put a single cell in my circuit, and I have a current flowing in the circuit because I have a power source. It's a very poorly drawn circuit. I'm going to place a resistor into this circuit with resistance R. And I'll complete the circuit. Actually, I'm going to add something else into the circuit that I'll discuss soon. But I'll add another resistor with resistance little r into the circuit. And basically, the EMF here is the energy provided by the cell and converted to electrical energy so that the current I can flow through the circuit from positive to negative. Remember, we're considering conventional current, which is the flow of charge from the positive terminal of the cell through the circuit components back to the negative terminal. Now, we have to understand that in reality, all power sources will have some internal resistance, some resistance that exists within the power supply itself. So all cells, all batteries have an internal resistance. That's why I've labeled this resistor little r. So that's the resistance that comes from the power supply itself. And this resistance we call the internal resistance. Now we sometimes, actually quite often, we ignore the internal resistance of a cell because it's usually quite small in comparison to the resistances of the entire circuit. So if R is very large in the circuit, then little r is going to be fairly insignificant. If I were to measure the potential difference across this cell, I'd find that it actually reads VR, where VR is the voltage across the resistor. And this is called a series circuit, by the way. And a series circuit is one complete loop. All my circuit components lie one after the other. And so I can see that I have a cell, and then I have a resistor with resistance capital R, and then an internal resistance little r, but all of these things lie in one loop. And so this is called a series circuit. Everything follows each other. So the current only has one path that it can take. And anything that looks like this is called a series circuit. And so the potential difference across the resistor is the potential difference across the cell when I connect a voltmeter across the 2 points in the circuit. Now the EMF, because there is a power or there is a voltage drop across the cell, the EMF, the total energy supplied per unit charge, is the energy supplied per unit charge for all the charges going across the big resistor and also across the internal resistance. So V across big R and V across little r. Remember that we have these resistors in series, which are now potential dividers, and we learned that in the previous section. And so VR is equal to the EMF minus the potential difference across the internal resistance of the battery, which even though is very small, we cannot say does not exist. And what we call this is the terminal potential difference. And we call it the terminal potential difference because it is the potential difference that we measure across the terminals of the battery, across the terminals of our cell, the positive and negative terminals, when the circuit is closed. When the circuit is closed, I don't read the EMF of the cell. The value that you see on your battery, the 1.5 or 3 volts, depending on what type of battery you're using, is not what I measure. When I open the circuit, the internal resistance disappears. All I measure is the EMF, since there isn't any current flowing in the circuit and the internal resistance is removed from the circuit. So if I close the circuit, allow current to flow, what I actually measure is known as the terminal potential difference. And so what I can see if I apply Ohm's law is that if these resistors don't heat up that much, is the total EMF is equal to I big R plus I little r. Or I can simply say I into big R plus little r. And so this is the equation that I would use to relate the EMF to the current, the external resistance or the load resistance. Sometimes we just call this the load, easier than saying load resistance, and include the internal resistance as well. So E is equal to I into big R plus little r. And another little note that we have to remember is that for the power, that is the energy per unit time that is given to my resistor big R, is a maximum, and you're asked to remember this. It is a bit of mathematical work to show this, and so we aren't going to show it. But the power is a maximum, it turns out, when the load is equal to the internal resistance. So big R is equal to little r. And at this point, the maximum amount of energy per unit time is being given to the resistor. And that energy can be converted to heat. If the resistor was replaced by a lamp, it would be heat and light and so on. And so the maximum power through the resistor exists when its resistance R is equal to the internal resistance. And that's a good point for you to remember, because it's part of our learning outcomes that we know that fact. Now, onto some laws which regard the flow of current, or a law that regards the flow of current through a circuit. And this is called Kirchhoff's first law. I think it's also called the current law. And that's because it has to do with currents in a parallel circuit. Now, I said a series circuit is when all the components are connected one after the other. So current has to flow through each one of these components before getting back to the cell. The other type of circuit we have is a parallel one, where a current can flow, but instead of having just one path to flow through, the current can actually split into multiple paths. The number of paths you have depends literally on the circuit that you are connecting and what you require. But let's say the current coming into this branch is I. Since it has three ways to flow, and each one eventually will lead back to the battery, each path is a viable one. We aren't going to talk just yet about how it breaks up through these three paths, but the current will split through each one of these branches. And this we call a junction, meaning a point where it can break apart. And this defines what a parallel circuit is. A parallel circuit is any in which the current can split into multiple paths and pass through multiple devices. And Kirchhoff's first law basically says that the current flowing into a junction must equal the total current flowing out of that junction. So in this case, the total current I must be the total current I1 plus I2 plus I3, which kind of makes sense as you think about it. Current is simply the rate of flow of charge. We can't lose any charge flowing into the junction when we consider the current flowing out of that junction. So you have to know how to write this in words as well. And basically, and I'm going to write it in sort of an incomplete sentence here. The sum of currents into a junction equals the sum of currents leaving that junction. So it's the conservation of charge. We can't have charge disappearing halfway through our circuit. And so you can write this in a more complete sentence, more coherent way, but I'm just writing this for simplicity. So Kirchhoff also had another law, which, believe it or not, he called the second law. And Kirchhoff's second law of electric currents is more to do with the conservation of energy. So the first law is, well, easy enough. The current comes in, branches out, it must stay complete. It can't lose, charge cannot be lost anywhere in the circuit. It has to be conserved. The second law comes from, we'll write it down in words first because it's that important. The sum of EMFs in a closed circuit, and a closed circuit is anyone like we've shown, that's where current is allowed to flow. So the sum of EMFs in a closed circuit is equal to the sum of potential differences. So basically what this means is energy must be conserved. All of the energy provided by a cell must be used by the components of the circuit. And so all the EMFs, the sum of all the EMFs must equal to the sum of all the potential difference across different devices in the circuit. And so let's draw this to make it slightly more visual. So I'm going to draw a battery that is just two cells, and it's going to be a very uncomplicated circuit, a series circuit with two resistors, and we'll name them R1 and R2. So there's two objects that are resisting the flow of current, that are providing an obstacle for the current to flow, and the current goes from the positive terminal, we'll call it current I, through resistors R1 and R2, and then back to the negative terminal of the cell. The EMF of the first cell is epsilon 1, and the EMF of the second cell is epsilon 2. I prefer to use epsilon rather than E because I like reserving E for energies. Again, that's completely up to you. And so let's assume that I connect my voltmeter across R1 and I get a reading V1, and I connect another voltmeter across R2 and I get a potential difference V2. So what Kirchhoff's second law says is that if I add the EMF epsilon 1 to the EMF epsilon 2, what I should get is V1 plus V2. So energy is conserved because, remember, EMFs and potential differences are energies per unit charge. And so again, this can be written as IR1 plus I R2. So the statement itself is easy enough, but it's quite profound. It has to be that energy must be conserved. Okay, and we can see here that the cells are connected in the same way. Negative, positive, negative, positive. Okay. Both the cells are discharging across the two resistors. So energy is being given to charge as it passes through these cells, and energy from the charges are being lost through each of these resistors, and the energy is being transferred to heat. Then the charges move back and gain energy as they pass through the cells again. I'm going to change the picture very slightly and see if you can notice what I'm doing differently. I'm going to draw the exact same circuit that we have above. Two cells, i.e. a battery, two resistors. I'm even going to give them the same names to keep you happy. And nothing else really in this circuit. So can you see if anything is different in the circuit? Well, you'll notice that my cells look a bit different here. Everything else seems to remain the same. I still have the two resistors, R1 and R2. I connect a voltmeter across each of these resistors, and I still find that I'll read a voltage, although it might be a different voltage, V1 and V2, and the current is I. Notice, however, that I'm confident that the current is moving, well, in this case, anti-clockwise. But my two cells are connected opposing each other. I've got a negative facing a negative, and I've got a positive on the outside. So how do I know that the current is flowing anti-clockwise? So in this case, the larger EMF must be epsilon 1. Epsilon 1 must be greater than epsilon 2. It is a greater EMF, and hence it is overcoming epsilon 2, the second cell, and the current is flowing anti-clockwise. But what this means is that instead of cell 2 discharging, because current is flowing in the opposite direction to which it normally would, cell 2 is being charged. And so if you wanted to charge a cell, you would connect it opposite to the direction in which it would discharge. And so now the cell epsilon 2 is gaining energy from cell 1. So we can apply Kirchhoff's second law again, and epsilon 1 minus epsilon 2, because the net EMF now is epsilon 1 minus epsilon 2. Epsilon 1 has to do work against the series components, but also work to charge epsilon 2. So it's minus epsilon 2 is equal to V1 plus V2. So we're not violating conservation of energy in any way. And so the mathematics still holds, and this is IR1 plus IR2. So just an interesting application of Kirchhoff's second law when the batteries are connected in different directions, or the cells are connected in different directions. So have we learned anything special about the resistors themselves? Not really, because we've connected all our resistors in series. That's why we haven't really seen anything special. So let's define more clearly what happens when we connect these resistors in series. So in series, remember, components follow each other. So here's a resistor, poorly drawn, followed by another resistor, slightly better drawn. We'll just stick with two resistors for now, R1 and R2. So they need not have the same resistance, and they're in an electrical circuit which we neglect to draw. The potential difference across R1 is V1. Notice the pattern. The potential difference across R2 is V2. Now, if I wanted to find the equivalent resistance, what's the total resistance of this combination? So that is, how can I replace these two resistors by a single imaginary resistor with the resistance R and a potential difference V across them? How do I know what the total resistance of this combination of resistors are? Let's say I wanted to replace these two by a single resistor. So if I do a bit of mathematics, what I know is V is equal to V1 plus V2. the total potential difference across this combination is V1 plus V2. Again, resistors in series are potential dividers. So they're dividing the potential. But I remember from the mathematical notation of Ohm's law that V is equal to I times R, V is proportional to the current, and the resistance is not changing. So IR is equal to IR1. The current flowing through all of these resistors will be the same because the current flowing in a series circuit doesn't change. IR1 plus IR2. But wait, the current is the same on all sides. So what I'm left with is R equal to R1 plus R2. And then let's say I connected more resistors in series, 3, 4, 5, 6, however many, then the resistance would just be the sum of the individual resistances. And so if I want the equivalent resistance for resistors in series, I just add up the resistances of each individual resistor. So if I tell you here's 10 resistors in series, tell me the entire resistance of the circuit, you would add up the resistance for each of the resistors. 1 ohm plus 2 ohm plus 5 ohm plus 10 ohms plus whatever. Okay, and that's the equation that we use, which you will find in your formula sheet. That's the equation we would use to find the equivalent resistance when we have many resistors put together. So I could take out those 10 resistors and replace them with 1 with that equivalent resistance, and I get a potential difference V across the single resistor. Now for parallel, it becomes a little bit more complicated. But remember, for parallel, current splits. So current doesn't remain constant. So let's draw another circuit where current I comes in. There's a junction, which means the current must split. I'm again going to have two resistors, but they're going to be in parallel with one another, meaning they're going to lie in different branches. So if two components lie in different branches, we say those two components are in parallel with each other. They don't follow each other one after the other. So the resistor on the top is resistance R1 and the resistor on the bottom is resistance R2. So I'm going to say that the current breaks up into I1 on the top and I2 at the bottom. The currents then pass through the resistor, and when they join again, the current that leaves that junction, or rather leaves the parallel part of the circuit, is then again I, because I1 and I2 meet and they go off on their merry way, and they must be I for everything to be conserved. So how can I find one equivalent resistance that's going to represent this parallel combination? Now, as you can see, it's not going to be as easy. And let's assume that across this resistor is a potential difference V, meaning that across this entire combination will be a potential difference V. Now, going back to what I know about these circuits, I know that I must equal I1 plus I2 from Kirchhoff's first law. But again, if I think of mathematical formulation of Ohm's law, I is the total voltage V divided by the total resistance R, the equivalent resistance, whatever that may be. And this must equal to the potential difference V divided by R1 plus the potential difference V divided by R2. Now, why is V not changing? Because remember, for a parallel part of a circuit, the potential difference across each branch in the circuit remains the same. So the potential difference across R1 is V, and the potential difference across R2 is V, and the potential difference across the entire parallel portion of the circuit is V as well. And so for every part of the branch, the potential difference is V, hence the V's cancel, and what I'm left with is 1 over the equivalent resistance, the total resistance, is 1 over R1 plus 1 over R2, And guess what? If I were to add another resistor or many other resistors in parallel, what I'd find is that the total equivalent resistance, or rather 1 over the total equivalent resistance, is equal to 1 over R1 plus 1 over R2 plus 1 over R3 and so on. So the equivalent resistance has to be calculated with the inverse and is equal to the sum of the inverses of each of the resistances in that combination in parallel. So if I have 10 resistors that are all in parallel, I will have 10 terms on the right-hand side of this equation. And what I can notice from here is that the combination of resistors will be lower than the smallest resistance in that combination. And so if I wanted resistors to stack, and I wanted the total resistance to be higher, what I would do is I would use them in series. If I had many resistors, but I wanted the combined resistance to be lower than the lowest resistance, then I would connect them in parallel. And so it actually decreased the resistance by using many resistors in parallel rather than in series. So again, that formula is in your formula sheet, but you could very well be asked to show where it comes from. And so either using a diagram or simply explaining in words, you can do this mathematics and show why the inverse of the equivalent resistance is equal to the sum of the inverses of the different resistances. So this is great, but where can I possibly find this useful? Well, one application that makes use of the fact that resistors can be potential dividers is called a potentiometer. So basically, what is a potentiometer? So here's a circuit. I'm going to connect a battery, that is 2 cells, with the EMF E. Again, you can use E or the Greek letter epsilon. And in this circuit, I'm going to have a resistor R1 and another resistor with resistance R2. And flowing through the circuit, I'm going to have a current I passing through the series circuit back to the cell. This is a series circuit. And across R1, I'm going to measure the voltage, the potential difference with a voltmeter. And I'll get V1. And what I'm going to do across R2 is I'm actually going to connect a set of terminals. And I'm going to essentially use R2 as sort of my base of measurement. And that's going to have a voltage V2. And I'm actually going to do something different here. I'm going to make resistor R2 a variable resistor rather than just a fixed resistor. So the reason why this circuit is special is because, well, let's do some mathematics, shall we? We love mathematics. V1 is I, R1, and V2 is I, R2. So if I take the ratio of voltages here, I can get rid of the current. I can divide both these equations. V1 by V2 is R1 by R2. Great. So the ratio of voltages is equal to the ratio of resistances. But I also know that the EMF in this circuit is V1 plus V2. So you might have an inkling of where I'm going here. Okay. If I divide by V2, just doing a bit of extra maths, you don't need to know how to do this mathematics, but it's good to see where we end up. So I get E by V2 is V1 by V2 plus 1. Why all this complicated mathematics? I sometimes ask myself the same question. E over V2 is equal to, now why would I divide by V2? Because I know that the ratio of voltages, V1 by V2, there should be V2 here, is R1 by R2. Aha, so all I did was replace the V's by R's, plus 1. And so what I get is E over V2 is equal to R1 plus R2 divided by R2. Okay, so I haven't done anything special here. I just played with mathematics and yeah, kind of went around in circles until I come to an equation that doesn't seem like it's very impressive. But essentially, what this means is that if I rearrange this V2, the potential difference across the second resistor, the variable resistor, is the EMF E times the resistance R2 divided by R1 plus R2. So all of this mathematics, what does it tell me? And what does this have to do with the heading that I wrote, the potentiometer? Now, the potentiometer is a device in which the output voltage V2 can be varied. And it can be varied by varying this thing here, the R2. So if I vary the resistance of R2, I can vary the voltage across V2. If I connect V2 across any external device, that can become my EMF for any external device. I can connect that across a different resistor, a lamp, etc., and that can become my output voltage. So potentiometer is some device through which the output voltage can be varied. You can probably see now why this might be advantageous. And the types of potentiometers that we are going to discuss, well, there's only two that will really interest us for now, will be the thermistor and the LDR, the light-dependent resistors, can be used as our variable resistor R2 in the potentiometer. So that means if I can change or vary the amount of light or heat falling on my device, heat in the case of a thermistor, light in the case of an LDR, a light-dependent resistor, and use them as variable resistors in this potentiometer, V2 is going to be constantly changing. Why? Because R2 is going to be constantly changing. And so this output voltage, if I connect two terminals across R2, output voltage will change. And if that output voltage changes, I can use it to switch on or switch off external components in the circuit, which I physically don't have to go and interfere with the circuit for it to do so. And that's the advantage of a potentiometer. If the variable resistor is the one that changes with light and heat, I physically don't have to go and make changes to get the desired result, like I would do with a normal variable resistor or a rheostat, the old school rheostats. And so that's the basic application of the potentiometer. So now you can see going through this weird mathematics was to get us a form of the equation in which the output voltage across the second resistor is related to its resistance. And by changing the resistance, we change the output voltage, and I can use that for different applications. I can also use a potentiometer for something in the lab, and that is to compare potential differences. And again, you'll see this as part of your learning outcomes in your textbook, in your notes, in your resources, etc. How do I use a potentiometer to compare potential differences? So basically, again, we like drawing circuits in this topic because it helps us visualize what's actually happening in the problem. It's very easy to state what a circuit does, but it's a lot better to have a physical picture of what's happening. And so I have a circuit here where I actually have a power supply, which we're going to label as V. So that power supply has EMF V across the cell, and then lower in the circuit, I actually have two more cells. The first cell I'll call A, and guess what? It has an EMF EA and a switch which can turn on a second cell, B. Guess what? Its EMF is EB. Trying to keep things very simple here. And the output of these cells is connected to a galvanometer. So I haven't shown you the circuit symbol. It is a circle with an arrow pointing upwards on it. And a galvanometer is basically a very sensitive ammeter. So it measures slight fluctuations in current, which an ammeter cannot measure since it isn't sensitive enough. And to top it all off, we're going to connect a wire, probably a different kind of wire, so maybe I should draw it in a different color. A wire through the middle, running to the middle of the circuit as we look at it. And then I have a cable or a sliding contact, called a sliding contact because it's free to slide and clamp on to different points of the wire, connected to the galvanometer. And so we call this contact a sliding contact because we usually slide it along the wire to different points. This weird meter is called a galvanometer. Measures small currents and small changes in currents which an ammeter cannot. And here, choosing between the two EMFs is a two-way switch. So this whole setup is a potentiometer that we use to compare the EMFs of two cells, in this case EA and EB. Now the length of wire between one end, which is the end where the switch is, and the other end where the sliding contact is, we're going to call LA. Right, so that's the length of the wire. So basically in this experiment what we do is we know the EMF of EA. Maybe we use a battery of known EMF, but we don't know the EMF of cell B. And so EMF EB is unknown. So we can use this potentiometer setup to find the EMF of cell B. So what we do is we adjust the length A. We call it LA when A is in the circuit. And we wait until the reading in the galvanometer, the current in the circuit, falls to 0. So as we move the galvanometer along the wire, the resistance in the circuit changes because this wire has its own resistance. And so we eventually find that this galvanometer reading falls to 0. So we adjust the length of the sliding contact along the wire until we get a value LA. And we read that value of length using a meter rule or something maybe more accurate. And so what we find is that the EMF EA is proportional to the length LA. So this means that EMF EA is proportional to the length LA. Apologize for the break in transmission there. And we then do the same when we connect cell B into the circuit, and we adjust the length again of the sliding contact, LB, until again the galvanometer reads a 0 current. So I is equal to 0 again for cell B, and this implies that the EMF of B is proportional to the length of B, the distance LB rather, the 0 point we call it. And what we get from these two expressions is that the ratio of EMFs, EB over EA, remember EA is known and EB is unknown, is equal to the ratio of distances LB over LA. And so obviously from here you can see that it's possible to calculate the unknown EMF. And so this may only be something that you would see in a laboratory, but it's an application of the potentiometer. So if you look at the complicated setup again, we can set this up fairly easily in a lab, and you would be expected then to find the unknown EMF with the known EMF EA and the ratio of the 0-point distances, LB over LA. And so this is one of the applications of a potentiometer to compare potential differences. And so this was a crash course on the topic of DC circuits. A lot more in-depth problem solving is required. But if this video is helpful, please leave a like or a comment down below and subscribe to the channel if you aren't already. And I guess I'll see you next time on Everything is Relative. That's all from me for now. I'm Mr. K. See you next time.